All right, so we're going to finish up reactions of alkynes. I wanted to put reactions of alkynes when we talked about reactions of alkenes, but we just ran out of time in lecture, so we're going to split it up, have them separate. And again, this is at the elementary organic level. I'll be posting this online, so if you're watching this and you're an Organic 1 student, the way we talk about reactions in Organic 1 is different than the way we talk about reactions in elementary organic. So just keep that in mind if you're watching this online. We're only going to do 2 reactions of alkynes. We're only going to do 2 reactions of alkynes in elementary organic. We're going to do hydrogenation and halogenation. And again, please keep in mind, this is for elementary organic. Right? This is not Organic 1, this is for elementary organic. We're doing hydrogenation and halogenation. So let's refresh our memory. What is hydrogenation if we're doing an alkene? What's hydrogenation a reaction with? It's a reaction with H2, right? And what's halogenation a reaction with? Group 7, so it could be Cl2, Br2, right? So any halogen. So these, I think, are pretty self-explanatory. Right? The major difference between hydrogenation of an alkene versus hydrogenation of an alkyne is instead of having one H2 molecule, you've got to have 2 of them. Why? Because you've got a triple bond here. Right? So if you react 1 molecule of H2, that reduces you down to a double bond. And then the second one reduces you down to a single bond. Right? So you're just taking that triple bond and you're reducing it all the way down to an alkane. Okay, so the only difference here is you have to have 2, right? You have to obey law of conservation of mass. If you've only got 1, then you'll be left with an alkene. But if you have 2 molecules, then you get your alkane. Okay, so it just takes you all the way down. Again, any substituents you had would go as well, right? So for instance, if there was a bromine on this, there'd still be a bromine here. That's going along with it. So make sure you add hydrogenation to your chart, if you're keeping track of your chart of reactions. Your reactant would be some sort of alkyne and 2 molecules of H2, right? What would your products be? It would be an alkane. Nothing fancy to worry about in terms of like Markovnikov's rule or anything like that. Just make a note to yourself that any substituents you had on the original alkyne would be on the alkane that gets produced. And also bear in mind that the way you started numbering in the alkyne, if I asked you to name the product, may not necessarily be the same way you number, right? Because if we were naming the reactant, you're going to number to give the triple bond the lowest number. But once that triple bond's gone, if all you're left with is, say, a substituent, if it was number 1 on the left, number 1 might now be right. So just keep that in mind. And then here's the only other reaction we're doing with alkynes in elementary organic. Again, the coefficient here needs to be 2, right? Because if you react 1 Cl2 molecule, you would get 1 and 1, right? And so you react 2 of them and you get 1, 1, 1, 1. Right? So you end up with tetrachloro or tetrabromo or whatever. Okay? So if you're keeping up in your chart, again, you need to have your reactant being this, and then some sort of halogen. Oh, and don't forget your catalyst. I forgot to list the catalyst. The catalyst will here be the same as in hydrogenation of an alkene, so platinum or palladium or heater pressure. Okay, this one doesn't require a catalyst. No catalyst needed. And then when you name this, the way you name it, you know, where carbon number 1 is going to depend on where that triple bond was in the molecule, right? You want to number it accordingly. So these are the only 2 that we are doing. And again, this figure is from your book. We're only doing 2 in elementary organic, hydrogenation and halogenation. H2, don't forget the coefficient of 2. And then Cl2 and Br2 are your most common. Right, so you could call it bromination, that'd be fine. You could call it chlorination, that'd be fine, right? Because that's just meaning that you're using chlorine as a halogen. That just means you're using bromine as a halogen. So if you're doing your homework and it says, write a reaction for the bromination of blah, 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 right? That's a halogenation reaction where bromine is the halogen that's being used. No catalyst needed for the halogenation, but you do need a catalyst for the hydrogenation. All right, so I'm going to pause the recording, let you try these two, and then also name your product. All right, let's go over these. I think I've got enough room on the screen here. I'll make it work. So let's practice naming the reactant too, just for good practice, because it's always good to work on naming, because it's always going to be with us. Are we going to begin numbering from the left or from the right? From here? Are you sure? 1, 2, 3. 1, 2, 3. Okay. Why did you pick this side?
Because it lets the substitution right.
Good. Okay, so what's the name of this? What kind of group is that first?
Methyl.
All right, so that would be 2 methyl.
3
hexyne, right? You also could have called it 2 methyl hex dash 3 on, right? If you want to split it up. When you're doing the online homework, it calls it this, doesn't it? It doesn't call it the split up one. I didn't think it did because your online homework goes with your book, and your book calls it that. But just so that you've seen it, other books may call it that. So what are we going to get when we react this? First of all, what kind of reaction is this? This is hydrogenation. And we left off the catalyst. What would our catalyst be? We could use platinum, palladium, nickel, heat, right? Pick one. So what's our product going to be? What's going to happen to the triple bond? It's going to go away, and we're going to be left with 1, 2, 3, 4, 5, 6, and then don't forget our methyl group. Right. So 2 methyl hexane. Okay. Let's number this one just for the practice. Where do we begin? Here, 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 here.
I think on the right or left it's the same as that.
Between here and here you're choosing? Now remember, the triple bond's got to get the priority. If we begin numbering over here, 1, 2, 3, 4, 5, the triple bond's on carbon 5. If we begin numbering here, the triple bond's on 1, 2. So we want to begin numbering from the left. So 1, 2, 3, 4, 5, 6, 7. Now we could have gone 1, 2, 3, 4, 5, 6, 7, 2, right? That would have made no difference. So what kind of group is this? Ethyl. And this is a methyl. So the name of this is 5-ethyl, 4-methyl, not hex, heptine. Heptine. Okay. So what kind of reaction are we carrying out here? Halogenation. I also would have accepted bromination, right? And so what's going to happen to the triple bond? It's going to go away, and what's going to be in its place? We're going to have a 7-member chain, right? 1, 2, 3, 4, 5, 6, 7. And let's go ahead and put our substituents that we had to carry with us. So carbon 4 has a methyl, 1, 2, 3, 4, and 5 has an ethyl. And then what's going to be on the old 2 and the old 3? 2 bromines on each, right? Because one goes here, one goes here, and then from the second molecule, another one goes here, and another one goes here. All right, so where do we begin numbering now? Number from the left. Right? 1, 2, 3, 4, 5, 6, 7. So we've got 4 bromos, right? So that would be 2, 2, 3, 3, what prefix? Tetrabromo. Then what? 5-ethyl 4-methyl heptane. Ran out of room. Good. Is a catalyst needed here? Nope. Remember, that's a test that you can do in the lab really quickly to tell if you've got an alkane or alkene/alkyne, right? If you add Br2 and it goes immediately clear colorless, you know, okay, I had at least an alkene. You'd have to do further testing to distinguish if there's an alkene versus an alkyne. But whether or not you have an alkane versus something saturated versus something unsaturated, that's a quick lab test you can do. Good. All right. Now, we are going to do one little bit. It's introduction to the Diels Alder reaction. It's just an introduction. Okay? The reason I say intro is because this is actually a Nobel Prize winning reaction. That's why it's named specifically for the discoverers. We're calling it intro, okay? Because this reaction has high stereo specificity. In other words, remember when we talked about enantiomers, right? You can make multiple enantiomers from products using Diels Alder. So you can get into some pretty complicated Diels Alder reactions. We're not getting into the stereochemistry here, okay? We're not looking at enantiomers. We're not looking at coming in from one face of the molecule versus coming in from the other face. We're just looking at kind of the overall picture, okay? It's a really neat reaction. And so I think when we talk about alkene reactions, it's a neat one to talk about. But when you go on to take organic, you'll study the stereochem of Diels Alder. But we just really want to introduce it, just so you can see the idea of what it entails. All right, that's all that we're going to do in this class. So I'm just going to give myself some blank to write on here. Okay, so what you need a diene, and we typically draw them like this. Right, a diene is a molecule with 2 double bonds, and this is the simplest diene you can have, right? You can't have a diene any simpler than that. And you also need an alkene. That's the simplest alkene you could have, right? You can't have an alkene simpler than that, because that's 2 carbons with a double bond. Okay, this is called a dienophile. Dienophile. Right? Phile means lover. So the diene and the diene lover. We just call it an alkene, right? And so this is a reaction. And again, when you take organic, you'll study the full mechanism in excruciating detail. All right? You're going to produce a generic product every time. The generic product. Okay, so basically what happens is here is going to form a double bond, a single bond is going to form between here and here. This double bond is going to get pushed to between here and here, and then a bond is going to form between here and here. Okay? So if you label your diene carbon A, B, C, D, and then on the alkene E and F, your generic product A, B, C, D, E, and F. And notice a bond formed between A and F. That's where this ring gets closed. This double bond gets pushed between B and C. So that's where this comes from. And then this bond between D and E forms, and that's what closes your ring. Right? So you get a generic product that's going to look like that in some way. But you've got to have a diene, and this is the simplest diene you could have. And you have to have an alkene. Again, that's the simplest alkene that you could have. And then any sort of substituents that you want to be on your product, Well, if you just make sure to put those on your two molecules you're beginning with, you could figure out what you needed to work backwards. So let's pretend that we want, let's pretend I want this. Let's just make it easy. What would my alkene and the diene need to be? Well, you can work backwards, right? If you just break this down, A, B, C, D, E, F, right? So let's work backwards. And by the way, this is what we're doing tomorrow in our enrichment. I'm going to give you a molecule that I want, and you're going to come up with a reaction that would make it. So that's what we're doing tomorrow in our enrichment. All right, so I want this molecule. So what do my diene and what do my alkene need to look like?
Won't the alkene just be just the double bond only? Well, is that the one that'll have the bromine on it?
Yeah, so look at where it is, right? The bromine needs to be here. And where does another bromine need to be? On D, right? You see how we can put those two pieces together? Again, we're staying super simple in Diels Alder. We're not getting into anything complicated. We're not looking at stereochemistry. We're not doing anything fancy. But I like to teach this when we talk about alkene reactions, because this is an alkene reaction, right? It's a reaction of an alkene and a diene. And you're going to see it in great detail, actually in organic too, probably, depending on where you go. Might get covered in organic one. Probably is going to get covered in organic too. I like to introduce it because it's a neat alkene reaction, but in elementary organic, that's as complicated as we get. Okay, so you can use it to do what's called synthesis, right? Where if I want a specific product and I know what it looks like, I can calculate backwards what I would need to begin with. And tomorrow in our enrichment, like I said, that's what we're going to be doing. Now that we know all these reactions, we can predict what two things must I react to get a desired product. That's a big part of organic chemistry. So that's where this is going to stop.